This is your presenter Asloob Mudassar, and I am presenting slide number 132 of the course on laser physics. Question is, what is mode locking? How it is achieved? Discuss its frequency and time domain pictures. The answer is, mode locking is a process in which the longitudinal modes of a laser are made to oscillate with a definite phase relationship, and this phase relationship is such that the phase difference between any two consecutive modes is constant and the same for all the oscillating modes. We know from the theory of longitudinal modes that the frequency difference between any two consecutive modes is constant and is the same for all modes. Let us represent this frequency difference by delta nu. So from our previous knowledge that the slides that I have presented earlier, we know that the longitudinal modes has a fixed frequency difference between them. That is delta nu. From one mode to the next mode is fixed and constant. So if these longitudinal modes, in addition to being they are separated by a constant difference in frequency, if they have a definite phase relationship between them, that is the phase difference between any two consecutive modes is constant, then we say that the laser is mode locked. We shall go through the details in the meaning of the mode locking. If a laser is oscillating with a large number of modes, I am talking about a large number of longitudinal modes, say n modes, with equal amplitudes, say E naught, but with random phases, even then the output beam from a random beam, even then the output beam, though random and spiky, is periodic with a period equal to tau p, and tau p is given by tau p is equal to 1 over delta nu. Each individual spike in the random intensity has a duration delta tau p is equal to 1 over delta nu L is equal to 1 over n times delta nu, where capital N is the total number of longitudinal modes and delta nu L is regarded as the total bandwidth of the modes. So you see that here we are assuming that n longitudinal modes are oscillating in the laser cavity. And each mode is separated by a frequency equal to delta nu. And that each mode has a constant amplitude equal to E naught. That is, if there are n modes, then each of the n modes has an amplitude equal to E naught. Even then, we would notice that although the phase relationship between the modes is random, then of course we can observe a periodic output from the laser with a period tau p, which is equal to 1 over delta nu, where delta nu has been defined as the separation between two consecutive modes in frequency domain. And delta tau p is then the duration, that is, each individual spike in the random intensity has a duration delta tau p, which is equal to 1 over delta nu L, and that is equal to 1 over n times delta nu L, delta nu. So delta nu L is regarded as the total bandwidth of all the modes, and delta nu, you know, that is the separation between the two modes. Figure 1 shows the normalized plot of intensity from a laser with n longitudinal modes, each of amplitude equal to E naught, with randomly distributed phases. All modes with the same phase and randomly distributed phases add to produce constant amplitude denoted by A of t. All modes with the same phase and randomly distributed phases add to produce resultant amplitude is denoted by A of t. So let me show you first figure 1. The caption of the figure is periodic intensity output pattern. Periodic, you see that here I am using the word periodic. Although there is not a fixed relationship between the longitudinal modes, even then I am talking about the periodic intensity. Periodic intensity output pattern from a laser with large oscillating modes, which is equal to number n, with the same amplitude E naught and with the random phases. So you see that I have plotted normalized intensity. A square of t is actually the intensity as a function of time divided, and I have normalized it with the maximum value with the amplitude of each mode, which is E naught. So by the intensity of the individual mode. So this is A square of t is the intensity of all the modes combined together divided by the intensity of the individual modes. So we have this a plot of the output intensity from the laser, and this is the normalized intensity. So you can see that you can look at this pattern. This is a randomly occurring pattern. So you can see that spikes are occurring randomly. For example, this spike, these are the spikes occurring randomly. But you know that after a time tau p, which is equal to 1 over delta nu, and this delta nu, you know that the separation between the two consecutive modes is given by 2L, is given by C over 2L, and since delta nu is occurring in the denominator, so we have 2L over C. So this is tau p. And you know that after the tau p, the time I have indicated from the beginning of the pulse to the time dotted line indicates the time period, the time tau p. You see that after this time, the function is repeating. And you see that this whole pulse has been repeated over here up to the end. So I have shown actually two periods of oscillations which are periodic. So one period is over here and the other period is over here. These are two periodic pulses coming out from the laser having randomly occurring spikes. So these you see that you can see these are the randomly occurring spikes. And I have also shown you delta tau p. You can see over here that is the width of an individual spike. Delta tau p is equal to 1 over delta nu L, where delta nu L is actually, which I have, you see that I have mentioned what is delta nu L. Delta nu L is regarded as the total bandwidth of all the modes. So in other words, you can say that a delta nu L starts from the delta nu L is actually the total bandwidth of all the modes. And then you can see that here we have assumed that that there are n modes and each mode has an amplitude equal to E naught, and the phases and the longitudinal modes are randomly phased. That is, there is no fixed phase relationship between them, and we can say that this is a unmode logged output from the laser. But you see that even we can see that there is a periodicity occurring in the output laser beam, although in each period the spikes are occurring randomly. But of course, now you see that this output, that is A as a function of time, that is the amplitude, but I have plotted here the intensity, which is A square of A of t, where A of t is actually the sum of amplitude of all the longitudinal modes. You know that when we are summing all the longitudinal modes by accident, some of the modes would have same phase relationship, but generally the phase relationship is random. So adding them all the modes, all the amplitudes of the modes, and then taking the square of that one, you get the intensity A square as a function of time, and you are normalizing this output intensity of the laser by the factor E naught square, which is the intensity corresponding to the individual longitudinal mode, and then we have this plot. So remember that this plot is even periodic, even when there is not a phase relationship, a fixed phase relationship between the longitudinal modes. Even you can see the periodicity between the two, you see that between the two set of pulses coming out from the laser, they are periodic with a time period tau p. If the phases have definite phase relationship, you see that in the previous plot we discussed that the phase relationship is random and the amplitude is fixed. Each mode has an amplitude E naught, but the phases between them is random. Now we are talking about if the phases have definite phase relationship. That is, if the longitudinal modes have definite phase relationship, that is, if the laser is mode locked. So you see that here you can see the definition of the mode locking. The mode locking means that all the modes have the same phase relationship between them. So that is, if the laser is mode locked, the output will be the sum of powers in each mode. That is proportional to n E naught square. Now we consider how mode locking is achieved in frequency domain. So one thing that I want to mention over here, that if the phase relationship is random, we can add the amplitude. We don't need to add the amplitudes, we need to add the intensities. So let me say this sentence again because this is very much important. If the modes do not have a fixed phase relationship between them, then we can add those modes on the basis of intensity. That is, we shall add the intensity of a mode 1, then the intensity of a mode 2, then the intensity of a mode 3. And all these modes will be added on the basis of intensity. But if there is a fixed phase relationship between them, that is, if the laser is mode locked, then we need to add the individual contributions from the mode on the basis of amplitude. That is, we shall add the amplitude of mode 1 to the amplitude of next mode, then the amplitude of the next mode, and these amplitudes are complex. That is, they have the amplitude part plus they have the phasor part. So the amplitude and phase, which means that the complex, then if in the case of mode locked laser, the amplitudes of the individual longitudinal modes will be added on the basis of complex amplitude. Now let's discuss the mode locking. Now we describe how mode locking is achieved in frequency domain. Let us discuss the mode locking of odd number of modes. For example, capital N is equal to 2n plus 1. That is, in the cavity we have 2n plus 1 number of modes. That is, the total number of modes is capital N, and this capital N is an odd number. So there are odd number of modes. For example, 51, for example, 53 or 55 or 67 or 71 or 83 and so on. So capital N should be a mode number here we are assuming, which are oscillating with the definite phase relationship. And we are assuming that the central mode, which is the n plus 1th mode, for example, the first mode is located on the rightmost, on the leftmost side. Then the next and the last mode is located on the rightmost side of the mode's positions. Then you know that the central mode, which is the n plus 1th mode, will be located in the center. So about this center, half of the modes, that is n number of modes, that is a small n. Here I am talking about small n. That is a small n number of modes are occurring on the left of the central mode, and small number n of the modes are occurring on the right side of the central mode. The phase relationship between the two consecutive modes is phi I, which is the phase value of the ith mode, minus phi of I minus 1, which is the phase of the I minus 1th mode. So the phase difference between these two consecutive modes is equal to phi is equal to constant. And here I can stand for any of the mode. for any of the 2n plus 1 modes. The mode picture when they have equal amplitudes is shown in part A, and when they follow Gaussian distribution is shown in part B of figure number 2. So let me show you that figure first. For example, this figure, let me read the caption first. Longitudinal mode distribution with constant amplitude in A. For example, you can see that the constant amplitude, there are 2n plus 1 modes, n modes. This is the central mode. The central mode has a frequency omega naught, and on the right side of the central frequency we have n modes, that is a small n, and on the left hand side we have n modes equal to small n, and the total modes in this are 2n plus 1. And you know that E naught is the amplitude of each mode. This is E naught. So all the modes in the first case, in case number A, have equal modes, have equal amplitudes. And you know that this delta omega L is the line width of the mode profile. So this is the mode profile, and this is the bandwidth, that is delta omega L is the bandwidth of the mode profile. And here I am plotting these modes in terms of the angular frequency omega. You can also plot this in terms of the linear frequency delta nu. And in the next plot, you see that the amplitudes of the modes are following the Gaussian distribution. That is, the central mode has the maximum amplitude, and then you know that the amplitudes are decaying on the right hand side and on the left hand side following a Gaussian distribution. And you know that the bandwidth of these modes are, again you see that represented by delta omega L, and delta omega is actually the frequency separation between two consecutive longitudinal modes, and omega naught represents the location of the n plus 1th mode, that is the central mode. So first of all, we shall discuss the case with equal amplitudes. The mode picture when they have equal amplitudes is shown in part number A, and when they follow Gaussian distribution is shown in part number B of figure number 2, which I have just discussed. The electric field in the output beam is the sum of the electric fields corresponding to the individual modes. Now you see that we are adding we are finding the resultant amplitude by adding the individual electric fields of corresponding to the each mode. And this addition on the basis of the electric field is due to the fact that there is a fixed phase relationship. So we can say that these modes are coherent in the sense they have a fixed relationship with respect to their neighboring modes. So we are now going to add them on the basis of electric fields of the individual modes. And this E of t, which on the left hand side of equation number 1 is actually the total electric field, the sum of all the complex electric fields of each mode. And on the right hand side we have the summation representing the parameter p from minus n to plus n, representing 2n plus 1 number of modes. So here you can see that E naught with a subscript p, just in order to show that you can put a different subscript of p, for example minus n, starting from minus n and going up to the plus 1 value. But you know that this is only for the purpose of labeling. But you see that E naught is actually the amplitude which is constant for each mode. So effectively this P of P as a pre-subscript of E naught is actually an amplitude of each mode which is equal to E naught. Then you know that this is the E to the power iota omega naught is actually the term due to the central mode. So this is due to the central mode, because the frequency of the central mode is omega naught. And this vector, which is e to the power p times delta omega into t, you know that delta omega is the separation between the two modes, two consecutive modes, and p is, you know, that is the parameter running from minus n to plus n. And so with this one, you are actually, when you run this index p, actually you are contributing in the summation the other modes. For example, if p is equal to minus n, then you are considering the minus nth mode. And if p takes the value plus n, then you are considering the rightmost longitudinal mode, which is the plus nth mode. So in fact, if you combine these two exponential terms, you have iota outside the parenthesis, which is omega naught plus p into delta omega, and t is outside the parenthesis. So this is actually effectively omega naught plus delta omega. Of course, with the p will remain the same. So these two actually will give you the contribution of different modes. So when you run the parameter p, index p, then of course you are actually summing up. You are writing up the amplitude of each of these modes. So E naught with these two factors, and this is the phase factor. You see that e to the power iota p. So when the index p is changed, the phase is also changed. And it means that the phase is fixed because phi is fixed, phi is fixed. P is just a parameter, an index parameter, but the phase phi is fixed from one mode to the next mode. That is, if p is equal to 1, then the phase is e to the power iota phi. If p is equal to 2, then the phase is e to the power iota 2 phi, which is the phase of the next mode. So it means that from the first mode to the next mode, the phase is constant. As we have mentioned over here, that is phi I minus 1 is equal to phi is equal to constant. So this is the phi we have taken as a phase parameter. So you see that this term is actually a complex amplitude. So, and this sigma summation sign represents the addition of the complex amplitude. And you know that these are the complex amplitudes. Now, from these complex amplitude, we can separate out e to the power iota omega naught t, because the summation is not applicable to this parameter, to this quantity, and the rest of the quantities on which includes parameter p and have been summed under this summation sigma sign. Now we can write this parenthesis containing all the complex amplitudes to be equal to a of t. So a of t is actually the resultant amplitude, and then multiplied by e to the power iota omega naught will give you the complex resultant complex amplitude of all the longitudinal modes added together. So that is the output field. This is the output field. That is, the output field in a mode locked laser may be considered as a sinusoidal wave oscillating with the frequency of the central mode with the modulating amplitude A of t. So this A of t is actually the amplitude of the modulating wave, because this is actually the result of the addition of the of all the complex amplitude of the longitudinal modes. And this e to the power iota omega naught, if you take its, for example, part, either the sinusoidal part or the sinusoidal part, then this becomes a sinusoidal wave, for example sine of omega naught t, or you can also write it as cos of omega naught t. Then you see that sine of omega naught t will be multiplied by this modulating amplitude. So this term can be interpreted as that is, the output field is in a mode locked laser may be considered as a sinusoidal oscillating sinusoidal wave, that is this wave, sinusoidal wave oscillating with the frequency of the central mode omega naught, for example, with the modulating amplitude given by A of t. So now we are going to discuss A of t further, because we, for example, from this one, the shape of the function A of t is not clear. So we want to actually find out the shape of the function A of t. So we are going to discuss A of t in the next slide, for example, over here. So this is the A of t. Here you see that I have red marked IP, that is iota p, on both exponentials, because you see that here you can see Okay, so the parameter p or the index p will run from minus n to plus n, and this is a of t on the left hand side. That is the sum of all the complex amplitude is mentioned over here in equation number 2. In equation number 1 and equation number 2, the central mode corresponds to the value of p is equal to 0. So you know that this central mode, which I have mentioned over here, and we have separated it out, that is e to the power iota omega naught t. Actually, this also corresponds to the value when we have the p is equal to 0 parameter. So in equation number 1 and 2, the central mode corresponds to p is equal to 0. Let us express equation number 2, that is this equation, in a transformed time domain t prime linked with the time domain parameter t through the relationship. Now, for example, if you take ip as a constant factor, and if you take, for example, t also common. So, for example, if you add these two exponentials, take ip as a common factor and also t as a common factor on the right hand side, take ip as a common factor on the left hand side, and take t as a common factor on the right hand side, then you will have omega, then you will have t plus phi over delta omega, and this t plus phi over delta omega is labeled as t prime. So now we are going to use t prime, which is equal to t plus phi over delta omega. And this factor is very obvious from the fact that adding the powers of these two exponential functions, taking ip common on the left hand side and t common on the right hand side, you will notice that we have this term appearing there, that is t prime is equal to t plus phi over delta omega. So t plus phi over delta omega is being referred to as with the new variable t prime. Now we have represented equation number 2 in a parameter t prime. So a of t prime is equal to this summation from p is equal to minus n to plus n, and then we have e naught e to the power iota p delta omega into t prime. So this has enabled us to simplify the calculations, and also we can write it in the form of single exponent with the use of t prime, because now t prime contains the information of the phase of the wave also. And since the phase is constant, so we have written it in the form of t prime. The right hand side, that is this one, together with the summation sign, this is a geometric progression and can be summed up easily. And equation number 4 will take the following form. So after you sum up this, you will get this form. So a as a function of time t prime is equal to e naught into sine of 2n plus 1 times delta omega by 2 into t prime divided by sine of delta omega by 2 into t prime. So we can obtain from this to this one. And this has also been discussed in the appendix. Let me show you this in the appendix. So in appendix 1, we have again this term. And you know that here I have expanded this one. So I have E naught separately. And then you have these n terms. And of course, these n terms, because these are the exponential terms. And the p is equal to 0 term has been separated out. That is E naught. When p is equal to 0, we have the value E naught, which is E naught over here. And the rest of the parameters have been mentioned over here. So with the negative index, p is going from minus n to 0, we have the negative index. And when p is going from running through the positive values, we have this term here. Now we can apply the summation of this one to these two are the geometric series, and the sum of these two geometric series is given by separately. So this is the geometric series corresponding to the terms in black, and this is the geometric series corresponding to the term in red. Now you see that you can rearrange the terms in the following form. That is, you can use subscript n will be multiplied over here, and this superscript, sorry, n will multiplied by over here. Then you will have this one, and you see that multiplication of n appearing as the power of the exponential factor, and of course n is also appearing over here, and the rest of the quantities are unchanged, except that we have, for example, from this factor in the denominator, we have taken this e to the power iota delta omega t prime divided by 2. This has been taken as common factor, and the rest of the two factors in this bracket is shown over here. If you multiply this factor inside this parenthesis, you will get back to this result. And similarly, from the denominator over here, from the red term, you can also this term as a common e to the power minus iota delta omega t prime divided by 2. You can take this factor common, and the rest of the two factors will appear over here, because if you multiply this factor inside, you will get the denominator in the red backward. So you see that this is the transformation that I have made. Now the further simplifications are required. Now you see that I have also taken this term as a common factor, that is e to the power iota n delta omega t prime divided by 2. I have taken this factor as a common from the numerator, because if you multiply this factor inside, you will get the same term. Similarly, I have taken this factor, that is e to the power minus iota n times delta omega t prime divided by 2, as a common factor, and then from this square bracket, because if you multiply this inside, you will get the factor backward. And then you see that these are the rest of the terms that I have written. And these two terms is what I have cancelled with the term in the numerator. For example, this term, which is e to the power iota delta omega t prime divided by 2, you can cancel this term with this term e to the power iota delta omega t prime, or you can take it in the numerator and subtract the arguments. Similarly, this factor can be cancelled out with this factor, and after cancellation, you have this result. That is this result. Now you can combine in the next result, you can combine these two terms. That is, this exponential and this exponential can be combined. Similarly, this exponential term and this exponential term can be combined together, and this is now the final result, because you have n plus 1 over here, and similarly you have combining these two, you have n plus 1 over here. Now you see that you will notice that apart from this factor and apart from this factor, the other factors are common to each other because they are similar. They are exactly each other. That is, this factor in black is the same as this factor in red. So I can take this factor and this factor common from these two terms, which I have shown over here. For example, this one as a common factor. So let me show so that you can understand. So this is a common factor from the two terms, which I have taken on the right hand side, and the left of the two terms are this. I have also taken E not common on the left hand side, and then you are left with two factors. One black factor is coming from the first this term, and this red factor is coming from this term. And the other terms, that is the two terms are common, and we have taken them outside. Now you can do the multiplications. That is, you have this term in the parenthesis summing up two terms. We have a sum of two terms in the parenthesis, and we have also sum of two terms in this square bracket. Now I am going to carry out the multiplication of these two parentheses, these two brackets. One is the parenthesis, the other is the square bracket, and the terms have been written. Well, those which are multiplying with the red, I have shown them in red, and those which are multiplying with the black, I have shown in black. And this factor which was in the denominator, I have written it as such. that is e to the power iota omega t prime divided by 2 minus e to the power minus iota delta omega t prime divided by 2. So now I can simplify the result in the numerator. So I can combine these two terms. The rest of these terms are here. Now I am going to divide the numerator by the denominator. So this is the denominator. If you divide this one by this term, by these two terms, you will get this. And if you divide the parenthesis by this term, this will cancel out, you will get minus 1 over here. Now you have to E naught plus E naught. If you take E naught common from these two, here you will have plus 1. This will be cancelled out by minus 1 over here, and then you will left with this term, E naught into this. So you see that in the numerator, you can divide the numerator, these two terms in the numerator by 2 iota. Similarly, you can divide the denominator by 2 iota. And then you can write the numerator by sine of 2n plus 1 into delta omega into t prime divided by 2. And similarly, the denominator by dividing it 2 iota, you can write it sine of delta omega time t prime divided by 2. And numerator is divided by 2 iota, denominator is divided by 2 iota, so the mathematically it would not make any difference, and then we can write these exponential terms in terms of the sinusoidal terms. These sinusoidal terms can be written in more explicit form as this. So you see that this is the amplitude that we have obtained in equation number 5. This is the resultant amplitude. And you know that here this resultant amplitude depends on the value of 2n plus 1, where 2n plus are the number of longitudinal modes. But if you find the corresponding intensity by taking a square of this quantity, then you will notice that in the square, a squared quantity will appear. That is, you have a sine squared quantity, and in the denominator you have sine squared quantity, and here this quantity will be E naught square. So if you have a square and divided it by E naught square, then you will have the normalized intensity. So let me go back to equation number 5. For example, this equation. So from equation number 4 to equation number 5, I have given you the proof that how we can obtain equation number 5 from equation number 4 by summing up the geometric progressions. If the mode logged condition in equation number 1, so you know that this equation number 1 is the mode logged condition, because here this is the phase which is constant, and we are adding the modes, we are adding all the modes on the basis of their complex amplitude. This is the addition. So we are adding all the complex amplitude on the basis, all the longitudinal modes on the basis of complex amplitude. It means that we are talking about the mode locked condition because the phase is constant. Okay, if the mode locked condition given in equation number 1 is expressed in time t prime, the output amplitude E as a function of t prime will be proportional to A of t prime. So this was our resultant, this was our total amplitude, and this was proportional to, you know, that A of t prime, as obvious from equation number 1. So look back to equation number 1, you will notice that E of t prime is now proportional to A of t prime. The normalized intensity, which is given by the A square of t prime divided by E naught square, the plot of this intensity versus t prime has been shown in figure number 3. That is this figure. Let me read the caption first. Time behavior of output intensity normalized with E naught square for the case of n longitudinal modes with equal amplitudes and individual phases locked. That is, this is the output from a laser which is mode locked. And this was the output from the laser, which is unlocked. So this is the output from the laser, which is mode unlocked. And this is the output from the laser, which is mode locked. You notice that here I have plotted a square of t prime divided by E naught square. And you see that the value of this peak is proportional to 2n plus 1 squared. Here we are also plotting this intensity unit, a square of time divided by E naught square. But this is unmode locked laser. Output from intensity output from an unmode locked laser. And this is the output intensity from a mode locked laser. This is the intensity, depends upon 2n plus 1, and the square of this is the amplitude, depends upon the value of 2n plus 1, and when we take the square of this one, we have the amplitude of each peak proportional to 2n plus 1 square. So here again you can see that tau p is the separation between these two modes, between these two peaks. Tau p again given by delta 1 over delta nu, and delta nu, which is the mode separation between two longitudinal modes, is given by 2L C over 2L. Since delta nu is in the denominator, so we have 2L over C. Delta tau p is actually the full width half maximum of each peak, because these pulses are periodic, and the separation between them is 2L over C. And this is delta p, delta tau p, which is the full width half maximum of each peak. And the time parameter from 0 to the foot of this peak is a tau prime p. So tau prime p is the time between the maximum of the peak to its first minimum. This is tau prime p. And this tau prime p can be approximately equal to delta tau p. So here you can see that this tau prime p is approximately equal to delta tau p. And this is the output from a mode locked laser, having all the longitudinal modes having equal amplitudes, and the individual phases are locked. The first peak corresponds to t prime is equal to 0 when the denominator vanishes. You see that the denominator of this vanishes at t prime is equal to 0 and t prime is equal to pi. When t prime is equal to pi, both the numerator and the denominator will vanish out. So the first peak corresponds to t prime is equal to 0 when the denominator vanishes. The denominator also vanishes for the case of the second peak, which occurs at delta omega divided by 2 into t prime is equal to pi. So the denominator will vanish at time t prime is equal to 0, and when the time t prime will follow this condition, then again the denominator will be equal to 0. For all values which are equal to n times pi, that is all values equal to pi, integer multiple of pi, then of course the denominator will be equal to 0. But since we have shown only the two peaks in plot number 3. So I am going to discuss only two values of time when t prime is equal to 0 and when t prime satisfies this condition. So the time separation between the two consecutive mode locked pulses is therefore given by. So this is tau prime is equal to 2 pi over delta omega. And this is equal to 1 over delta nu is equal to 2L over C. And you know that this tau p, which is the separation between the two pulses, is what I have shown in the previous slide. For example, over here, you can notice this tau p, separation between the two peaks of the pulses. And you know that we have found this time from our mathematical equations. For example, from this one, that is the denominator vanishes at time t prime is equal to 0, and at a time t prime is equal to when t prime satisfies this condition. So subtracting the two times, one t prime from here, the other t prime over here, subtracting these two t primes, you will get a tau p is equal to 2 pi over delta omega is equal to 1 over delta nu is equal to 2 L over C. At time t prime is equal to 0 and t prime is equal to 2 pi over omega, delta omega, the denominator and the numerator both vanish. And the peak amplitude value is given by A as a function of t prime, and its peak value is equal to 2n plus 1 times E naught. The plot of figure 3 is for arbitrary number of modes greater than 51, for example. The pulse width delta tau p at full width half maximum may be approximated to be equal to tau prime p, where tau prime p is the time corresponding to the first zero of the main lobe. That is from the maximum of the main lobe to the first zero. And this is what I have mentioned over here also. For example, over here, that tau prime is equal to delta tau p approximately. The pulse width delta tau p at full width half maximum may be approximated equal to tau p prime, where tau p prime is the time corresponding to the first zero of the main lobe. That is from the maximum of the peak to its first zero. To calculate tau p prime, we set a of t prime equal to 0, which vanishes at this one. So from the numerator, because the numerator will vanish out when it satisfies this condition. That is the numerator of this function. That is when we want to make a of t prime to be equal to 0. This is only possible when the numerator is equal to 0, and that will only possible when the numerator satisfies the condition, when the argument of the sine function in the numerator is equal to pi. For example, this condition. So you can solve this condition for the value of tau p, where tau p is equal to delta tau p, and you can say that delta tau p is approximately equal to tau p prime is equal to 2 pi over 2n plus 1 times delta omega. And you see that this delta tau p is also equal to 1 over delta nu L, where delta nu L is the total bandwidth of the laser. Total bandwidth. Delta nu, when we total bandwidth of the laser. It can be approximated to the gain line width delta nu of the laser also. You know that in while discussing the theory of the lasers in many of the previous slides, we talked about the gain line width of the laser, and there we used the parameter delta nu naught to represent it. So here you can also represent a delta nu L, having the same meaning as the gain line width delta nu naught. So you see that you can find the necessary parameters in the mode logged in the output intensity of the mode logged laser output. For some lasers, for example, semiconductor laser, solid state laser, dye lasers, etc., delta nu L could be very large. So the pulses of a very short width can be produced down to a few femtosecond, because the separation of the width will then be very small, because the delta nu L is very large. In that case, delta nu, that is the separation between two consecutive longitudinal modes, will be very small. And they could be, we can obtain pulses. Of course, the pulses will even then be very small of the order, and very short width of the pulses can be produced down to femtoseconds. So under mode unlocked condition, the average power of a laser is proportional to 2n plus 1 times E naught square. Whereas under the mode locked condition, the peak power in the pulses is proportional to n plus squared times E naught square. So you see that this is the factor which is squared in the mode locked case. Thus, a mode locked laser produces 2n plus 1 times more power compared with its unlocked counterpart. That's why mode locking is essential in order to produce increased power from the laser output. You see that before this, up to this point, we have discussed the longitudinal modes having a constant amplitude equal to E naught. Now we are going to discuss the amplitudes having following Gaussian profile. Now we consider Gaussian shape of the longitudinal modes as shown in part B of figure 2. So let me go back to figure 2 and show you this is the Gaussian profile. So these are the longitudinal modes, but you know that at the central mode having the maximum amplitude E naught, and when you go away either to the left or to the right, the amplitude is going to decrease following a Gaussian distribution. Now we assume the Gaussian shape of the longitudinal mode as shown in part B of figure 2. The amplitude of the qth mode can be written as. So I am just now talking about the qth, talking about the not amplitude, but you can say that the intensity corresponding to the amplitude of the qth mode, which is given by EQ squared is equal to E naught squared into e to the power minus 2q delta omega over delta omega L squared, then log of 2. And if you want to talk about the amplitude, you need to take the square root of both sides of this equation. But here you can say that this is not the amplitude, but this is the intensity corresponding to the qth amplitude following a Gaussian distribution. This is the intensity of the mode, or E naught is the amplitude at the center of the Gaussian profile, and EQ is the qth mode, amplitude of the qth mode, where delta omega L, which I have shown over here, is the full width half maximum bandwidth of the spectral intensity. E naught is the amplitude of the central mode, which has been assigned zero phase. So the phase reference is with the central mode. The central mode is assumed to have zero phase, and the phases of the other modes will be measured with respect to this central mode. Equivalent of equation number 4 can thus be written as. So let me show you equation number 4 first. This is equation number 4 that was written when all the modes have the same amplitude E naught. But now the amplitudes are different from mode to mode following a Gaussian distribution. So now I am writing their resultant amplitudes. Again, the resultant amplitude will be done on the basis of amplitude addition because the phases are fixed. So this is again a case of fixed phases, but the amplitudes are now following a Gaussian distribution, and the summation of the complex amplitude will now be governed by the term on the right hand side. So we have Q as a pre-subscript, and we have also a Q as a post-subscript. So EQ into e to the power iota q into delta omega into t prime. Here you see that this Q has a label index with the Q as a subscript, and the index is running on the parameter Q from minus infinity to assuming that there are infinite number of modes there. So it means that each EQ will be different when the value of Q will be different from the index. So each EQ has a different value. And you know that if you sum up all the infinite number of modes from minus infinity to plus infinity, you will have the resultant amplitude represented by A as a function of t prime, shown in equation number 8. If the number of modes is very large, delta omega will be very small, and the summation can be approximated by the following integral. So you see that we can replace this summation sign shown in equation number 4 by the integral. So we have a of t. Now we have dropped the t prime parameter because in the integration that would not matter. So a of t is approximately equal to the integral of eq multiplied by the factor e to the power iota q delta omega times t, and the integration is done with respect to the parameter dq as shown in equation number 9. The laser pulse intensity a square of as a function of time is a Gaussian function of time given by. So you see that what you need to do is that substitute the value of a of t, substitute the value of eq. You know that eq is given over here. Take the square root of both sides of this equation to find the value of eq. Substitute the value of eq over here in this integral. That is in over here. Substitute the value of eq over here and then perform the integration. You will get a as a function of time, then take the square of both sides, you will get the intensity. That is the a square as a function of time will be proportional to e to the power minus square of 2t over delta tau p multiplied by log of 2. I am not going to perform this integral because this will be a very lengthy process, where delta tau p mentioned over here is equal to 2 times log of 2 divided by pi into delta nu L. And if you evaluate these numerically, you will find that it is equal to 0.44 divided by delta nu L. Equation number 9 can be interpreted as, this is equation number 9, and can be interpreted as the field amplitude A of t, that is this field amplitude, can be obtained from the Fourier transform of EQ. This is EQ, and this whole integral is actually the Fourier transform of EQ. So A of t can be obtained from the Fourier transform of EQ. And what is EQ? Magnitude of the spectral amplitude. That is the magnitude of each spectral mode. That is each longitudinal mode. And delta tau p is related to delta nu L through the relationship. That is delta tau p is equal to beta over delta nu L, where beta may take a value around unity, that is close to 1, depending on the shape of the spectral intensity distribution. A pulse with these characteristics is said to be transformed limited, because you see that it involves the Fourier transform, and this spectral intensity distribution will be limited by the by the transform. So it is referred to as that the pulse with these characteristics is said to be transform limited. And these are the characteristics that I have mentioned, the delta tau prime for each of these, and I have also mentioned the intensity as a function of time when the modes have distribution, when the magnitude of the modes follow Gaussian distribution as shown in part B of figure number 2, and when there is a fixed phase relationship between them, that is the laser is mode locked. So now we are going to discuss another thing, very important thing. Now we present the time domain picture of the mode locking. Two output intensity pulses separated in time by tau p, which is equal to 2L over C, and L is the cavity round trip time, and 2L over C is actually the cavity round trip time. That is the time taken by the light to travel one cavity round trip is tau p, as shown in figure number 3. We have shown it in figure number 3 also. Let me show you again. So this one, tau p has been shown equal to 2L over C. Now we present the time domain picture of the mode locking. Two output intensity pulses separated in time by tau p equal to 2L over C are shown in figure number 3. Each pulse has a duration delta tau p equal to 1 over delta nu L, which in space domain has a width delta z found from delta z is equal to C times delta tau p. So this is the width in space domain. Delta z is equal to C times delta tau p. Delta z is usually much shorter in comparison with the length of the laser cavity. In laser cavity, there is only one ultra short laser pulse oscillating back and forth. In a laser cavity, there is only one ultra short laser pulse oscillating back and forth. The output thus consists of a train of pulses separated by the time equal to the cavity round trip time. So remember that since the pulses are separated by a time equal to the cavity round trip time, so it means that at only one ultra short laser pulse will be oscillating back and forth within the laser cavity at a time. If a laser is mode unlocked, that is the random mode phases are present with the modes, that is the modes are present with the random phases, then placing a fast shutter in the laser cavity, the mode locked operation can be performed or can be obtained. So it means that the mode locking can also be obtained with an unmode locked laser, provided we place a fast shutter in the laser cavity. So placing a fast shutter in the laser cavity will enable us to obtain mode locked operation. A mode unlocked laser consists of many intensity spikes as shown in figure number 1. If the shutter, so let me show you figure number 1 again. Okay, you can see that there are many spikes. This, and repeating, and then the repeating after that. So a mode unlocked laser consists of many intensity spikes as shown in figure number 1. If the shutter is just opened when a spike is at its doorstep and is closed just after the spike as just after the spike has passed, the spike has passed, not as passed, the spike has passed through it, then only this spike will propagate in the laser cavity. That is, you are placing a very fast shutter within the laser cavity, and the laser and the shutter just opens when it receives the spikes and just closes down when the spikes has just passed. So if the shutter is just opened when the spike is at its doorstep and is closed just after the spike has passed through it, then only this spike will propagate in the laser cavity. If the shutter is at one of the cavity mirrors. So if we have placed a shutter at one of the cavity mirror, this is the description relevant to that. The shutter opens and closes only for this spike, and thus this spike will oscillate back and forth in the cavity. The exit beam will then have pulses separated in time by 2L over C equal to the round trip time of the cavity. This situation is depicted in part number A of figure number 4. The shutter is periodically opened with a period capital T equal to 2L over C. So let me show that how we can place a fast shutter to obtain a laser to obtain mode locked pulses from unmode locked laser. And this is shown in figure number part A of this figure. So let me read the caption of this figure first. Use of a fast switching shutter to obtain mode locked pulses from an initially unlocked laser. Initially the laser is unlocked, but when you have placed a switch, then only the desired pulses will pass through the switch and the laser becomes locked. Shutter close to one of the cavity mirrors is discussed in part number A. That is the shutter placed, this is the shutter, shutter placed close to one of the cavity mirrors. For example, here the shutter is placed close to mirror 2. The part number B is shutter is in the center of the cavity. Here you can see that the shutter in the part number B, the shutter is in the center of the cavity. For example, this is the shutter. So the left mirror is at a distance L by 2. The right mirror is at a distance L by 2 from the shutter. So this is mirror 1 at a distance L by 2 from the shutter. This is mirror 2 at a distance L by 2 from the shutter. This is the shutter. So you can see that there are two pulses passing through the shutter from opposite directions. And what is the case number C is shutter at 1/3 cavity length from mirror 2. So this is mirror 2 and this is the shutter which is placed at a distance of the cavity at a distance equal to L over 3. And the other mirror, that is mirror 1, is of course at a distance equal to 2L over 3 from this shutter. Since we are obtaining the output from the mirror 2, so we can say that it is at a distance L over 3 from mirror 2, this shutter. And here again you see that there are three pulses now. The two pulses are crossing the shutter in opposite directions as in case number B. And you know that there is a third pulse also present somewhere. And the fourth case is the D case, shutter anywhere in a ring cavity laser. So D is the case of a ring laser, of a ring cavity laser, and this shutter can be placed anywhere. So the two pulses you know that are passing through it always if you place a shutter anywhere in the cavity. The two pulses will cross this shutter in opposite directions and they are separated by distance LP divided by C, where LP is the length of the perimeter of this cavity. That is, if you start from mirror 3, then this distance plus a distance up to mirror number 1, then from a mirror to mirror 1 to mirror 3, this total distance is the perimeter and this distance is LP divided by C. So the pulses will be coming out from this ring cavity separated in distance, separated by LP over C, separated in time by LP over C. So if you obtain a laser from the condition shown in number 3, then of course the separation between the pulses in time will be equal to 2L times divided by 3C. And if you are obtaining, you see that here three pulses are present. If you are discussing the case number B, then of course the two pulses are crossing the shutter from opposite directions and the separation between the pulses will be L over C. And if you are discussing the case number 1, in which only one shutter has been placed very close to mirror number 2, only one pulse will be present in the cavity at a time, and then of course the separation between the pulses will be 2L over C. If the same shutter is now placed in the center of the cavity, the shutter needs to be opened periodically with a period capital T equal to L over C. In the first case, the shutter should be opened after this time. T is equal to 2L over C. And after the peak has passed, the shutter should be closed. So it means that only one peak will be oscillating under this condition in case number A. And that is a mode locked pulse. And the separation between the pulses is 2L over C because the shutter is closed at this time. Here, In the central case, when the shutter is placed in the center, two pulses are crossing the shutter in opposite directions and separated by a distance L over C. As you see that I have discussed the case B. This is a shutter placed at equal distance that is placed in the center of the cavity. Two pulses are crossing this shutter in opposite directions. It means that there will be two pulses present in the cavity at a time. So it means that the number of pulses that will be emitted will be double in the same time. That is, the time for each pulse separation between each pulse will be L over C. Two pulses, this is what I am talking about, the central case. Two pulses will oscillate and cross each other when passing through the open shutter, which closes just after the pulses have passed. The exit beam has a train of pulses separated in time by L over C. The situation is depicted in figure number B. Now I am going to discuss the third case, that is part number C. If the same shutter is now placed to a distance L over 3 from one of the mirror, for example, in case of a mirror number 2, or 2L over 3 from the other mirror, that is mirror number 1 in the present case in figure number in part C of the figure, and opened periodically with a period capital T is equal to 2L over 3C, then the three pulses will be simultaneously oscillating in the laser cavity. Two of which will cross each other when the shutter is opened. In the exit beam, the pulses are separated in time by 2L over 3C. The situation is depicted in part number C. You can see over here in part number C. That is, the three pulses are present. Two pulses will cross the shutter at the same time. So it means that in the cavity at a time there will be three pulses present. And the separation between the pulses is being narrowed down, and the frequency of the pulses has increased. The separation between the time separation between the two pulses will be 2L over 3C. Now we are going to discuss the case D. The part D of figure number 4 shows the mode locking situation, which is independent of the shutter position. You can place the shutter anywhere. The first, second, and third harmonics are controlled by the repetition rate C over LP, 2C over LP, and 3C over LP of the shutter respectively, where LP is the length of the perimeter of the ring cavity. So you see that you can control the number of, you can have a control on the harmonics. That is the first, second, and the third harmonics can be controlled by the repetition rate set by these parameters C over LP, 2C over LP, 3C over LP of the shutter respectively. So controlling the shutter at this speed or at this speed or at this speed, you can have three different harmonics oscillating within the cavity. Again, you can have a look at the situation in part number D. So this shutter can be placed anywhere, and you can control the frequency of these shutters equal to LP over C, for example, in this case. And you can have different timings for that one. For example, you can have C over LP, then you can have 2C over LP, then you can have 3C over LP to have three different harmonics to oscillate in the cavity. The situation is depicted in part number A is referred to as the fundamental mode locking. The situation in part number B and C is referred to as the harmonic mode locking. And the situation depicted in figure number 4 is referred to as the time domain picture of mode locking. So you see that we have discussed the time domain picture of the mode locking in much greater detail. You see that in the appendix I have established the connection that the amplitude in case of mode logged output will be proportional to 2n plus 1. and the intensity will be proportional to the square of this quantity, that is 2n plus 1 squared. And you know that this is what I have shown also over here. In the case of the output intensity from a mode locked laser, that the output intensity of the peak will be proportional to 2n plus 1 squared. But when we have unmode locked laser, then the output intensity will be proportional to only 2n plus 1. The proof of this one can be seen in appendix number 2. For example, this is appendix number 2. You see that here we are adding different longitudinal modes on the basis of intensity, not on the basis of amplitudes, because in the case of locked laser, the amplitude is random, and we have to add them in terms of intensity. So this is the intensity I naught sine of omega naught t is the intensity of the central mode. This is I naught sine of omega naught plus minus delta omega, and of course t should also be present over here, which I think I have missed over here. So t is also present. So this is the mode corresponding. This is the intensity contribution from the mode corresponding to by a separation of delta by a separation from the central mode by delta omega plus minus delta omega, and here time factor should also be present over here, that is I naught sine of omega naught plus minus 2 delta omega, and outside this bracket we have a time t which I have missed over here. Then you see that this is the contribution of the two other modes separated with the distance of 2 omega naught plus minus 2 delta omega naught. Similarly, at the end we have the nth mode unit, and we have added the nth mode over here. And if you can look that I have these modes, that is you have two sine values over here, sine function with plus delta omega, the other function is sine of a minus sine with minus delta omega, and if you add up these two sine functions together, you will get this function in red, 2 I naught into sine of omega naught t into cos of delta omega times t. Similarly, each sine function with plus 2 delta omega minus 2 delta omega will be split into two parts. We have sine of omega naught t plus cos of 2 delta omega t into t. Similarly, all the terms will be separated. And you know that sine of omega naught t is common in all these. You can take sine of omega, sine I naught into sine of omega naught t as a common factor from all these terms, and then you are left with these. And then you can have only cosine terms over here. You can take two factor common from all these cosine terms. Then you can write cosine terms in the exponential forms like this, but you need to write that we are considering RE, that is the real part of each term. So we have written them in terms of the exponential form so that we can do the manipulations very easily. And then you see that I have added all these exponential forms because this is a geometric series and have been added to show you terms like this. And then you see that you can do the mathematical manipulations very similar to the manipulations I have done for the case of mode locked amplitudes. So similar patterns, you can follow the similar patterns over here. These three red terms in the exponential patterns, the red have been combined over here. So here I have only made one approximation, that I have replaced this n with n plus 1, assuming that n is very large. So when n is very large, then addition of 1 to the parameter n would not make much difference, because I have done this one because I have a pn plus 1 appearing automatically over here, and I have considered the real part of this function, which is cos of this. And then you see that this parameter is the same as the parameter present over here. So you can combine these two formula through trigonometric function, which I have shown in green. that is this red and this blue have been combined to write the function as shown in green. Then you can multiply 2 and inside you have 2n plus 2, and I have ignored 1 over here again because I wanted to write in a meaningful form so that I can make a comparison with the mod logged case, because I am going to discuss this unmod logged case. So this factor should be actually 2n plus 2, but I have written it as 2n plus 1 because the addition of 1 would not make much difference. Now the next step will further simplify these. So this is the next step, and now you see that is I of t is proportional to this factor because this factor is constant at one value of time. But you know that this I of t can be written as to be proportional to this factor. Also, this is not constant but also proportional to that one. So here, so you can, if you go one step down to show the proportionality, you can write this that this I of t is proportional to I naught of sine of omega naught t divided by sine of delta omega, which I have written over here, and this sine function has been written over here. So if you go one step further down, you will see that I of t is proportional to this sine of a function, and you know that this sine function here I am talking about the intensity parameter. The intensity is proportional to 2n plus 1, has a dependence on the parameter 2n plus 1, whereas the amplitude of this is the unmod logged case. And you know that the mod logged case which I have discussed in appendix number 1, you will see that the amplitude is proportional to 2n plus 1. It means that the intensity of the mod logged case will be proportional to the square of 2n plus 1, to the square of 2n plus 1 factor. So that's why the mod logged, in the mod logged case you have a value greater than by a factor of 2 plus 1, that is the intensity of a peak in a mod logged case laser will be 2n plus 1 times greater than the intensity of the unmod logged case. So you see that I have discussed mod locking in much greater detail. I hope that this will be very useful for the readers. So this is the end of slide number 132.